let's get started. So before the exam, we talked about how to derive equations for 1 PG split hybrids. Today we're going to investigate 2 PG split hybrids, which includes both input and output split and compound split. Okay. By the way, we can actually create input and output split configurations with speed reduction gear. Okay. Okay. So two commercially known split hybrids are Toyota hybrid system, and well, here it says Allison hybrid, but yeah, compound, multi-mode compound hybrid system from General Motors. Okay, and General Motors actually have developed multiple many architectures, and they came up with 2-mode Allison hybrid and output split, multi-mode output splits, multi-mode compound split plus input split. So they have many architectures. But here in this class, we are going to look at these two architectures as a 2PG example. So far we looked at Toyota hybrid system as an example for 1PG system, but now we're going to look at 2PG split systems with clutches. Okay. And the way this works conceptually is that it has two clutches. Oh, by the way, this architecture is not currently used for mass production vehicles. This was early stage 2-mode GM was promoting. So that was back in 2005, something like that, before Voltec came out. Okay, and they actually applied this for large SUV and trucks. Okay, because large SUV and trucks have very, very low fuel economy. So they thought if we can improve fuel economy of SUV and trucks, that'll benefit a lot, because fuel consumption, absolute saving from hybridizing these larger vehicles will benefit consumers. But it turns out that SUV and truck buyers do not really care about fuel economy. So it didn't really work. But anyway, so that was, so marketing and engineering perspective can be different. So did you guys understand what I was explaining? So anyway, so SUV obviously requires large towing capacity and high tractive force. And they wanted to come up with high gear ratio. So this is also known as ECVT, right? Split hybrid is also known as ECVT, meaning that electronic continuously variable transmission, right? So what that means is it's a CVT, but electrically varying the gear ratio. But the 1PG systems usually have limited gear ratios. So it's usually more suitable for compact vehicles like Prius, light vehicles. But when you go to heavier, larger vehicle, you need higher gear ratio or range, wider range of gear ratio. So for example, so a small vehicle doesn't have to have, such a high force, high torque, right? But heavier vehicles really need that high torque and power, right? And usually this means amplifying torque. Amplifying torque means larger or wider gear ratio is needed, okay? Because the maximum vehicle speed is usually given, right? But anyway, to increase this torque amplification, you need higher gear ratio, but 1PG just couldn't do that. So what GM people came up with is two mode. So one for mid-high speed and one for low speed. Okay, so this is low speed mode and this is high speed mode. And by using these two clutches, you can actually create two different architecture from one architecture. Okay, so if you did not have any clutch, you will only have this mode, but by having clutch, you can actually have this mode as well, or vice versa. So this is a sort of schematic, cross-sectional view of the PG and the connections, but I hope you guys are now more familiar, comfortable with this lever diagram, right? So now x-axis is omega, right? And then we have y, that just means distance from relative distance between the node, right? But anyway, so when everything is at full stop, which is this lever, and as vehicle accelerates, which is done in low speed mode, these nodes will start move, and then once you approach some medium speed, you will move to high speed mode by disengaging this clutch and engaging this clutch. Okay, but what's interesting is you have two planetary gear sets, right? And then two clutches. So let's learn how this works a little more detail. Oh, before we get into more details, let's take a look at more background information. If you look at Toyota hybrid system, there are many variations. For example, you have Prius, right, which is the first hybrids, and then they moved on to Camry, which is full-size sedan, and then they moved on to SUV, a Lexus RX 400h, and then Highlander, Toyota Highlander. And then they also came out with GS 450h, which is Lexus. And this one, interestingly, this one is rear-wheel drive. This one is four-wheel drive. These two are front-wheel drive. Okay. And look at these numbers. Well, their rated power is quite different, right? And their engine is different. And their fuel acceleration performance is also different. Fuel economy is also different. By the way, these numbers are old information. Their numbers have improved significantly. But the size of the components is about the same. They tried to reduce the component size, but they're about the same. But anyway, so this lists up the type of motor they are using, so you can have a sense of how big those motors are. Okay. And you can see the point here I'm trying to get to is they're using different components, and they have different, they use different, they require different performance specification. You know, for front-wheel drive Camry will require different specification from SUV, and that'll also be different from performance sedan like GS 450 hybrid. So, but can they use Toyota hybrid system to cover all these vehicles? No, they couldn't. So what they had to do was they had to come up with variation of Toyota hybrid systems. Okay, so this was the early Toyota hybrid system, which uses one planter gear set. But later on, they came out with SUV with two planter gear sets. By the way, this one is two planter gear set put into a single component. I mean, single device. So you can see there is a planet and sun, and then this is ring. And you can see these two planetary gear sets share ring gear. Okay. So two planet, two sun gears are inside of one long ring gear. Okay. Interesting, right? And then rear wheel drive. Oh, by the way, for SUV, they added one more motor for rear wheel drive. So this is front wheel drive, okay? So they can actually create four wheel drive using 1, 2, and 3, okay? So in other words, there's this hybrid powertrain, and then there's one small motor in the back, okay? And for the rear wheel drive, obviously you need engine in front, so powertrain in front, and then you need to connect it with rear wheel drive, right? So how conventional powertrain does is they put engine and transmission, okay? And same applies to this hybrid Lexus. So this is transmission, which is hybrid transmission. So you can see this is generator, and this is motor, and connected to the rear wheel, and then here is engine. Okay. And this is simplified schematic of this transmission. Okay. So here's the engine. Here's the output. And then this is housing, fixed outside housing. And then motor 2, motor 1. And then you have one PG. And then you have here's one more PG. And then here is PG3. Okay. So this one has 3 PGs. Interesting, right? So what they did was they added one more PG here. One more PG here. To amplify torque and optimize component operation. Okay. By adding second PG, they can actually, have more design freedom, right? So they can optimize, performance, driving performance, and fuel economy. But that wasn't enough for high performance vehicles, such as rear wheel drive vehicles. So what they invented was they added one more PG, and then they added this clutch. But the role of second and third PG is the same. The role of this PG was speed reduction gear. Okay. So they used PG, but they didn't have to use PG, because speed reduction gear just means, simple fixed gear ratio. Okay. But you can do this using PG, right? input and output, right? And what I'm trying to say here is the second PG and third PG are used as speed reduction gear, but they are not used together. Either one is used depending on the speed. So if you think about it, now this is two-speed gearbox. Do you guys follow? 한번 다시 설명을 공문으로 하면은요. 변속기가 뭔지는 우리 배웠죠, 그죠? 뭐 1단이 있으면 감속기고 뭐 2개가 있으면 2단 변속기고 3단, 4단, 5단 변속기가 있죠, 그죠? 근데 그 변속을 하는 거를 이제 클러치 가지고도 이제 하고 뭐 여러 가지 방법으로는 할 수 있죠, 그죠? 근데 결국 여기서 하고 있는 게 그 변속 역할을 하고 있는 거예요. 그러니까 그 스피드 리덕션 기어라는 게 결국 그 변속 기어비인데 그 기어비가 여기서는 하나만 있어도 괜찮았는데 여기서는 2개가 필요한 거예요. 왜냐면 이 토크를 앰플리파이를 해야 돼서 이 토크를 앰플리파이 하면 기어 맥시멈 속도가 여기까지밖에 안 나와요. 자동차 속도가. 그럼 자동차 속도를 더 올리려면 기어비를 낮춰야 되는데 그러면은 결국에는 이 토크가 낮아지는 효과가 나오는 거죠. 그죠? 그래서 여기를 올려야 될 때는 1단을 쓰고 여기를 올려야 될 때는 2단을 쓰고 그냥 기존 변속기랑 똑같은 거예요. The only difference is the CVT part, ECVT part, which is this part, right? But this part is just any conventional transmission, okay? And this slide shows there are multiple, variations, sub-configurations. There are many, actually. And let's take a look at Allison hybrid, okay, which is the two-mode, 2PG, two-clutch architecture, which gives us 2 modes, okay? So if you look, now we can see here is one PG. Here is another PG. And this is motor, right? And this is another motor, right? And then this is the output. Here's the engine. And then you have a clutch here. Then you have clutch here. If you draw a lever diagram, this converts into this lever diagram, but offers 2 modes, low speed mode and high speed mode. By the way, this low speed mode is 1 PG plus SRG. This high speed mode is compound split, meaning that it's got 4 four shaft. In this case, we have we are using second PG as a speed reduction gear or torque multiplication gear. But in this case, there's no ground, right? We have two connections. So now 2PG is now connected and they are moving together, okay? But in this case, there's only one connection. But one is grounded. So the way split powertrain, split hybrid works is conceptually like this. So this is very similar to Toyota hybrid system conceptually, but technically in detail they're different, right? They're different architecture. But power flow is actually quite similar. For example, oh, this is PDF. Anyway, so during region power flows this way, or power assist mode actually goes like this. And then split mode has this path, and then has this path, right? So we talked about power flow of split hybrids briefly, right? So the generator generates some of the mechanical power, converts into electrical power, and then traction motor gets that electrical power and propel the vehicle, right? So that's a split hybrid. And to understand how this two mode works, we need to look at the speed diagram, okay? X-axis is output speed, and Y-axis is input speed of engine and motor generator. So let's start with lower speed input split mode, and the vehicle is now at full stop, okay? So vehicle is here. So now everything is 0. And when you start the vehicle, of course you could start with EV mode, but let's say we are going to start with engine power, okay? And in that case, if you look at this speed diagram, this is the vehicle speed. If you look at this plot, the output speed linearly increases with output speed, obviously, right? Because they're the same thing, right? And then if you look at motor 2 speed, it's also proportional to output speed, but at higher rates. Remember, this PG is speed reduction gear, right? So speed is reduced. Right? Now let's assume that engine speed is constant. Now this is that. So omega E is constant. Otherwise we can't determine everything, right? This is 2 degrees of freedom system, right? Did we talk about this? Do you guys remember? What's the degrees of freedom of PG? How many degrees of freedom do we have? 준태 학생? 갑자기 잠이 또 확 깨죠. PG가 DOF가 몇 개일까요? 병준 학생 한번 답해 줄 수 있을까요?
2개로 알고 있습니다.
네. 왜 2개죠?
그 3개 중에 2개 정하면 한 직선 위에 있어야 되기 때문에 나머지 1개는 알아서 정해집니다.
네. 그 개념적으로 물리적으로는 설명을 잘 해줬는데 이제 수학적으로 설명을 하면요. 요거죠. kinematic constraint가 있어서 so this lever indicates that kinematic constraint, okay? So this, if we did not have the lever, then we have three DOF, right? But that kinematic constraint is making sure that this is on the line. This is on aligned, right? 그래서 스피드 2개가 정해지면 나머지 하나가 정해지죠. 그래서 2DOF죠. 자, 준태 학생, 다시 기회가 있습니다. PG가 2개 있으면 how many DOFs do we have?
두 개가 연결 안 돼 있으면 총 4개의 자유도를 가질 것 같습니다.
네. 2 더하기 2는 4죠. 근데 what if there is one connection here? let's say this is ring gear, ring 1, ring 2. 그럼 몇 개일까요?
세 개가 됩니다.
네. 자, 우리 더하기 빼기 재밌죠? 여기가 근데 왜 그럴까요? We have one more kinematic constraint, right? By connecting these two. So that's -1. What if we do this? And obviously it's 2, right? But what if we do this? 그러면 DOF가 몇 개일까요? Anybody? Neil, Sanmin, Jaewon.
I think it's 2.5.
Are you sure?
I
Are you sure?
think it's 2.5.
It's 2. Well, this is also another kinematic constraint, right? Omega C2 equals 0. So that counts to this one. So the point I'm trying to get to here is, no matter what, this they all have 2 DOF, okay? If you think about it, it has to, right? Because we have only 2 shafts, input and output, right? So we have engine as an input, and then we have vehicle as an output. And then rest, such as motor speed, should be automatically determined, but we can control the speeds by applying torque, right? Okay, anyway, so 1 PG plus SRG, 2 PG compound split, okay? Anyway, so let's move on. Now, high speed, okay? So now clutch 2 is engaged, clutch 1 is disengaged. Now let's do speed analysis, okay? So again, with respect to output speed, let's see how things change. So now engine speed is 0. X is output speed. So, so this is why I was saying 2 DOF, right? So omega E, omega out is determined, then we can determine everything else, okay? So let's say at mid-high speed, what happens to vehicle speed? It's still linear relationship, right? What about motor 2 speed? Well, now it gets a little tricky. We can't directly determine based on that output speed, but we can determine that based on input and output speed, because now this is one lever with 4 nodes. We're going to get to this, but we can actually lump these PG1 and PG2 into one lever with 4 nodes, okay? Now this is 2 engine vehicle 1, okay? Now the vehicle is the output. So this is linear, obviously. And if engine is constant, then we can find 2 and 1, right? And those are these 2 lines. This is 1 and this is 2. So as vehicle speed increases, motor 1 increases, but it's faster, right? But motor 2 slows down or can even reach negative, right? Because now it's going like this, right? Vehicle speed is increasing. So 1 is increasing, 2 is decreasing. Right? Any questions? Are you guys following? Yes, no, kind of, triangle, X, yes. 졸리지 말라고 재롱 떠는 거예요. 근데 좀 어렵긴 하죠. Especially if you have doubly background, this can be challenging to follow up. So I suggest you talk to your TA or myself if you don't understand, okay? All right. So same story goes, but this is a more detailed scenario. So starting from 0 speed, and now let's sort of think of a scenario that the vehicle accelerates, okay? So that's this. So at 0 speed, everything is 0 except for the engine, right? But if this is 0 and engine is rotating, then motor 1 has to be rotated at high speed, okay? Next, now vehicle is moving at, I don't know, 20 kilometer per hour. Now vehicle and motor 2 speed is increased, but that means motor 1 speed is now decreased because this is increased. And then if you increase vehicle speed further, now your vehicle and motor 2 speed increases further, but your motor 1 speed reduces further and actually reaches 0. Okay. And I don't think I talked about this a lot before, but what happens if generator speed becomes 0? Did I mention about mechanical point? No? Okay. But I did talk about power flow, right? So split hybrid has this power flow, generator generates power and then that's forwarded back to motor, right? And when generator power, when generator speed when omega goes to 0, the power goes to 0, right? Assuming 100% efficiency. This is 100% efficiency. So what that means is the power flow through the generator becomes close to 0, okay? And that's called mechanical point, meaning that all of the engine power flows through the mechanical path rather than electrical path, okay? And then here's the split, right? And then here's the merge, right? Anyway, so now motor 1 is now at full stop or close to 0, right? So the engine is running, output speed is rotating, but by the kinematic constraints, mg1 is non-rotating. That's an interesting point, right? And that's called the mechanical point. So there's no power flow through the mg1, okay? I mean, close to 0. And actually, this is a good timing to move on to the high-speed mode, okay? That's because at high-speed mode, if you draw this speed, if you do speed analysis, this is the intersecting point, right? So when this intersects, rather than going further, we want to switch to high-speed mode, high-speed gear, and now the the power train behaves a little differently, right? So in low speed mode, the input split mode, it would have been going this way and this way, right? But by disconnecting this and engaging this, now it's compound split architecture. And now the behavior is now different for a given input and output speed. Okay. So input and output is given, right? Input was assumed constant, and output is output speed. But now motor 2 and motor 1 changes its direction. So now motor 1 now moves this way and motor 2 now moves this way. For the mid and high speed, okay? So this is all mechanical stuff and speed analysis, okay? And, oh, by the way, at some point, when you have output speed equals input speed, motor 1 and motor 2 will also have the same speed, right? Because remember, this is the engine, this is output, right? So when engine and output is at the same speed, everything is aligned and all speed are the same, which is this point. Okay, I think this is good enough for now, and let's move on. So that was a little, that could have been a little difficult to understand. But now it's back to modeling part, which you guys are now familiar with, hopefully. So now we would like to develop model, right? So we want to derive the models just like we have been doing, right, last time. So we draw a free body diagram, we draw you know, torque and reaction torque, and then we drive Euler equation for all the inertia, right? So this is that, and these are the resulting equations. I'm not going to derive this line by line, you know, everything, but this is the final results. But interesting part is this is the dynamic equation, and these two are the kinematic equation for the PG, 2PG, right? So we have two kinematic constraints by the PG, 2PG, and then we have 4 equations. And if we rearrange everything in state space form, this is what it's going to look like, right? Again, we have internal forces, F1 and F2, which is in the PG itself. So 4 dynamic states and 2 internal forces. And then we have inertia matrix, right? And then we have the kinematic constraint. And then we have torque vector, input torque vector, right? So you can see the pattern is still similar, right? But previously, you had 3 states and 1 internal force, right? Now, you have 4 states and 2 internal forces, right? And that's because this is a 2PG system, okay? And this was for low speed mode. And now this is for high speed mode, because if you engage clutch 2, and if you consider high speed mode, now you're looking at different architecture. The powertrain is different, right? Because the connection has changed, right? So now you have to redrive everything and come up with the state space model. So you have each model for each mode. So 2 mode requires 2 models, because those are 2 different powertrain, okay? So you have low speed mode model, high speed mode model, and you need to switch between these 2 if you want to simulate this together, okay? And Tuma is actually investigating into this. Right, Tuma?
Yes.
And Tuma has had hard time, but it's almost finished. But it's interesting research topic. So now let's move on to compound lever analysis, okay? So now we need compound lever, okay? Why? Well, if you have 2 or more PG, then it'll be easier to visualize and model, okay? Because previously the way we draw using, you know, elementary 3 node based PG lever had to be drawn this way, right? Or like this, right? But for compound lever, we can actually simplify further like this. So we can combine, so R1 and S2, because omega R1 equals omega S2, right? So R1 equals S2, and these 2 are the same because they're connected. Mechanically connected means same speed. This is mechanically connected, so same speed. And then this one is determined by these 2 speed. This one is determined by these 2 speed, but they are related, right? So if you think about it, this can be combined, right? And when you combine, what's important is this ratio, okay? Because this is R1, this is S1, this is R2, this is S2, right? And this is a kinematic constraint, right? So this has to be always true. So now what that means is this ratio and this ratio is important. And this is called combined lever diagram. We can put 2 PG onto 1 lever, okay? The way we do this is pretty easy, actually. So like I said, this ratio has to be kept true at all times. So we just need to make sure the ratio is kept constant. And to do that, we just need to match the length of the lever equal, meaning that the summation of this 2 equals summation of these 2. So now this ratio becomes this ratio becomes that. Then now 3, 7, this, and that. Easy, right? Any questions? And when you do compound lever analysis, we need to define a few parameters, few variables. So we are going to define some variables with respect to the output. Okay, so think of the output vehicle as origin. Okay, so 0. Okay, and remember, this is still lever, right? And this is sort of distance, relative distance, or relative position, right? And this is still true. So if this becomes origin, now this distance is beta, and this is going to be alpha, and engine input to output is now 1. So what this is, we are going to normalize the distance from motor 1 to output divided by the input to output distance. Okay, and this distance divided by input to output distance. So if you divide everything by this distance, input to output, then obviously this is going to be 1, and that normalized distance is alpha and beta. Okay, by the way, the absolute distance is not important. I mean, it doesn't even exist anyways, you know, if you think about it. What's important here is the ratio between these 4 nodes. Okay, so we just introduced alpha and beta. And so this is a compound lever, which has 4 nodes. And we have 4 components usually, right? Motor A, motor B, or motor 1, motor 2, engine, and output. So we have 4 components to connect to, to this lever. So we have 4 nodes. So one component goes to each node. And this is called a compound lever or a compound split, right? And there are some special cases. For example, if alpha or beta equals to 0, meaning that if motor 1 or motor 2 is at the output, then it becomes input split, right? And if alpha and beta equals to 1, then one motor is also connected here. Then it's called output split. And you can realize this with 1 PG, right? Because you have 2 components on one node. Are you guys following? So if MG1 goes to this, then you only have 1, 2, 3 node, right? If MG2 is now on the input split input node, then you have 1, 2, 3 node, right? So now this becomes input or output split because you have 2 components on one shaft. Okay, and we can realize this using 1 PG. But we cannot realize compound lever using 1 PG because 1 PG has only 3 shafts. But compound lever has 4 shafts or 4 nodes, okay? So you need at least 2 PG and 2 connections, okay? But the connection could be anything, So there's a lot of combination, a lot of variations to create this compound lever. And so that's why there's a lot of variations in split hybrid architecture design space. And our lab actually investigated a lot into this design space, explored a lot of architectural study, and Tuma has been working a lot on that topic, and Tuma will give you a very, very nice talk, I think next week, right? Yeah. And I hope it's interesting to all of you. 다들 기대해 주세요. So, anyway, I think time is up. So I will stop here and I will finish rest of the materials on Thursday. Any questions before we finish? So before you come, please take a look at the rest of the slides, okay? Like I said, this material, now the lecture material is going to become a little more tricky and challenging to follow up, okay? So please take just 10 minutes or 15 minutes and take a look at the lecture materials before you come to class, okay? If you do so, you will probably understand much more from when I lecture, okay? All right. Any Any questions? Oh, I have one announcement. Last homework will be handed out today, and it's going to be due next Tuesday. And it's going to cover the material we talked about today, okay? And last week. Okay, so the modeling of kinematic, so drawing kinematic diagrams and modeling split hybrids. Okay. All right. So that's it from my side, and I'll see you guys on Thursday. We can actually visualize multiple PG with one compound lever that helps us to visualize things and analyze things. So this is especially useful when you have compound lever, meaning that you have two planetary gear sets and two connections. And then we can combine them two and come up with one lever with four nodes. We just need to keep the relative distance, the ratios. And then we defined alpha and beta, which is the distance with respect to output. So the output becomes origin, and the input becomes 1, and then motor 1 is alpha, motor B is beta with respect to the output. And when alpha or beta equals to 0, then it becomes input split. And when alpha or beta equals to 1, then the lever becomes output split. So input and out, you can think of this as input and output split is special case of compound split. Meaning that input and output split is subset of compound split. Okay. And let's start with input split, which we have been investigating a lot, which is one popular input split is Toyota system, and one well-known output split is Voltec first generation. Okay. So when alpha or beta equals to 0, then it becomes input split. And two components are connected to one shaft, and engine, and one motor is connected by itself. Oh, by the way, note that these values does have sign, meaning that this is origin, and beta in this diagram is negative. Okay, so alpha is positive. So this is positive, and this is negative. Okay. That way we can describe any compound lever, compound split architecture. And then just like what we have been doing, x-axis is omega. So in this example, this vector indicates speed of that node. So for example, this is ring, carrier, sun, and this becomes omega R, omega C, omega S, right? But torque has to be described by this vector or arrow acting on the node. So if you do not have, so let's say you draw a lever without any vector applied on the lever, then this can only describe the speed. But if you want to indicate the torque acting on the lever, then you need to draw that arrow. Okay. So this is how you can visualize torque acting on the lever and the resulting speed. Okay. And if you start using second planetary gear set, and especially if you're going to use it as a speed reduction gear, that means you need to ground one node. This is one example. And then originally, this vehicle was connected to here, but by using second PG with ground, it becomes speed reduction gear. And by connecting vehicle here, the speed becomes half of the motor speed, right? So it's the ratio between this and this, right? Because omega equals to 0 here. Everybody following? Okay, so last week we worked on steady state analysis, and we also worked on modeling of input and output splits. And what we are doing here is also similar work, but for compound lever, but in a more general way, meaning that using compound lever. So, and we can do lots of things using this compound lever approach, and you will find that out over the next few lectures. Okay. First, let's start with steady state analysis. So this is identical to the steady state analysis we worked on last week. So we have these relationships. So because all omega dot equals to 0, right? So all the summation of all the torque has to be 0, and summation of torque multiplied by, say, I don't know, distance r has to be 0. So this is moments, right? like I said, this is torque, but from lever perspective, this is, you know, visualized as a force, right? So if we take a moment about some point, then this is moment, and this becomes torque times R, where this is R, okay, right? So if you add all the moments, then it has to be 0, otherwise the lever will rotate, right? So if the steady state means lever is not moving at all, right? So in order to meet that condition, these two has to be true, right? And this is these two. And this is simply kinematic constraints, okay? But we have two equality conditions because we have two planetary gear sets. So we have 2 degrees of freedom because we have this constraints, and which gives us 4 equations. And I quickly mentioned about mechanical point, and the definition of mechanical point is when either motor A or motor B, speed becomes 0, okay? And this is defined as a mechanical point, okay? And Toyota hybrid system, 1 PG has 1 mechanical point, and Allison hybrid compound lever has 2. And you will see why. So mathematically, so this is the condition, right? Omega A equals to 0, omega B equals to 0, right? But when for the input split case where beta equals to 0, then you only have this equation. So you have 1 mechanical point. But when both alpha and beta is neither 0 or 1, then you have a compound lever and you have 2 mechanical points, which is these 2. So 1 and 2. Okay. So let's start with these 4 equations, and let's do a some steady state analysis. Okay. So when beta equals to 0, the 4 equations reduces down to these 4 equations. Okay. So if you just plug in 0 for beta, And then we can define Rn as omega I divided by omega out divided by alpha minus 1 over alpha. What does this mean? Let's start with this term, numerator. What's omega I divided by omega out? Well, Neil said R is gear ratio. Yes. What gear ratio? Anybody? I mean, what is omega I divided by omega out? What is omega out? It's vehicle speed, right? Output speed, right? What's omega I? It's input speed, which is engine speed, right? So usually, if you're talking about hybrid powertrain, and when we're talking about powertrain, usually engine is the input and vehicle becomes the output. And from that perspective, input speed divided by output speed is transmission gear ratio, right? So this is transmission gear ratio. And what's this? Well, if you go back, it's mechanical point, right? Meaning that when this condition is met, omega A or omega B equals to 0, right? In this case, omega A equals to 0. So we are dividing omega I divided by omega out, and we divide that by mechanical point. So what's that? Well, you'll see what that means in the later slides, okay? Just keep this in mind, and we are going to use this definition to make the analysis simpler, okay? So we have these 4 equations, and we are going to normalize speed, torque, and power, okay? But anyway, this mechanical point, we are normalizing transmission ratio with mechanical points. So this is transmission ratio normalized by the mechanical points, okay? And then now we want to normalize speed, torque, and power, okay? So that means we're going to divide omega A by omega I, torque A by torque I, and then we have power, okay? And if we, and in order to find the relationships for omega B and torque B, we need one assumption. Otherwise, we have too much freedom. So what that means is, if we assume this, then that means no battery power, right? Because oh, by the way, here is one. So here is the sign, so that torque and omega becomes, the power becomes positive, okay? But if you just include the sign as a part of the variable, then this is it. Then if we assume no battery power, that means there's no power coming in from the battery, then this has to be true, right? So we are making this assumption to see some steady state analysis. So we are assuming omega dot equals to 0. So there's no change in speed mechanically. And then we are also assuming there's no, battery power coming in. So if we have battery power coming in, if this was non-zero, then we have too many freedom, okay? So to make this analysis simple, and so that we can do analytical analysis, we are making these assumptions, okay? So if we assume no battery power, then we can compute these values, okay? So now if you look, all the variables are given. All the variables are now sort of model parameter or design parameters. Alpha was the distance. Alpha was this. Beta was this, right? So these were determined by the design, right? So for a given design, alpha is known. So this is known, right? And the only variable we have is Rn. But if you look at Rn, what is Rn? Well, alpha is known, but what's unknown is omega I and omega out. So two variables right? But by defining Rn, we are actually combining two variables into one. Okay, so we are only going to look at the ratio between omega I and omega out. So now unknown is one variable, Rn. Okay, so this Rn becomes independent variable. Okay, so now let's take a look at case study. Okay, so this is Toyota hybrid system with alpha equal to 2, alpha equal to 4, alpha equals to -2. The real Toyota hybrid system have about alpha equals to 2. Okay, and we are going to compare that with other gear ratios, okay, or other designs. Okay, and if you look, x-axis is Rn. So x becomes independent variable. Okay, and y is torque, speed, and power. Actually, let's look at this one first, okay, to make it easy to read. So normalized speed, think of it as divided by mechanical points, right? So we divide by mechanical points, so 1 is always mechanical points. Meaning that omega and power will become 0 at this point, right? Of A. And what does a large Rn mean? What does large Rn mean? And what does small rn mean? You have to answer this. Someone has to answer this. Who is that going to be? 룰렛 같은 거를 만들어서 딱 찍어야 되나? 랜덤으로? Volunteers.
기어비가 크고 작은 걸 나타내는 것 같습니다.
Okay, on the right direction. So what does that mean? I mean, can you elaborate more? Can you describe a little more in detail? Think of it from the input and output speed.
그 오메가 i분의 오메가 5로 그러니까 정의가 되는데 이 Rn 값이 큰 게 오메가 5가 작다는 거니까 비클이 속도가 낮으면은 이 값이 클 것 같습니다.
So yes, that was correct. So to summarize that, so there is two variables, right? Omega in and omega out. So this is only relative value, okay? Rn is relative value. But think of it as a scenario, okay? Situation. So Rn, large Rn either has to mean large omega I or small omega out, right? So there's two freedom, right? So to make this simpler to think of it as omega I, which is input or engine speed. Let's say engine speed is fixed, okay? I mean, it can change, but let's say it's fixed. Then what happens to omega out, right? Large Rn means what? Small omega out. Small Rn means large omega out. So that means small, so small omega out means low vehicle speed, right? Large omega out means high vehicle speed, okay? So as you go this direction, this means low vehicle speed, okay? As you go towards this direction, this is large vehicle speed, okay? So that's what it means physically, okay? And why, like I said, why are we doing all of this, you know? To make the analysis simpler and easier to visualize, we need to do lots of normalization, okay? So that the analytical analysis becomes, you know, feasible. Okay, so if you say high vehicle speed, low vehicle speed, then it'll be easier to understand. So when you accelerate vehicle, you are starting somewhere here and you're moving towards this way, okay? So now let's look at motor A operation, okay? So again, so think this way. So when vehicle speed is low, then motor A speed is high and motor A power is negative. But as you accelerate, motor A speed reduces and eventually approaches zero. And that's the mechanical point. Okay? And when you accelerate further, when vehicle speed increases, then motor A becomes negative and power actually becomes positive because torque was negative, okay? And let's look at motor B, which is motor. So motor A is generator here, motor B is motor, okay? When alpha equals to 3. So let's look at motor B case. This is a traction motor. And as vehicle accelerates, motor B speed increases, obviously, because it's connected to output speed. And the torque has to be reduced by by this constraint. Okay. And because power,
My mic is on.
because power is reverse of this power, right? Remember, PA equals PB, or negative PB, right? Because we are assuming no battery power. So this is simply reverse of this, right? Sign is reversed. So speed is constrained by the vehicle speed, or Rn, right? Independent variable. And then power is constrained, so your torque can be computed. So, and this is what you are looking at, okay? Oops. And this is the results, right? So normalized speed, torque, and power with respect to Rn, right? So transmission ratio, or you can also think of it as vehicle speed coming in. And you are looking at motor A and motor B behavior. At steady state, okay? No battery power, and omega dot equals to 0. So we can do this kind of analytical analysis if we make some assumptions. And this is very helpful, right? And you can see how power is flowing. So here, you know, motor A is working as a generator, but when you go beyond the mechanical point, now motor A becomes motoring, okay? But here, motor B was doing motoring, but beyond mechanical point, now motor becomes generator. And you can also see how operating speed changes with respect to Rn, or vehicle speed, and how torque needs to be, determined to maintain steady state condition, okay? But this is not always true, because we made assumption about the steady state condition, okay? A vehicle is highly transient, right? You can ask for high power, low power, you can accelerate, decelerate, your vehicle speed will change, engine speed can change, lots of things can change. So it's dynamic. But still, if you're cruising at steady state vehicle speed, say steady state engine speed, 0 battery power, then this steady state analysis is valid, okay? And this tells us a lot about how the system operates at steady state. And we don't have to do any optimal control or anything, right? No DP, not even simulation, All we need was these equations. That's it. And to plot this, plotting these two results, it takes, you know, I don't know, 0.001 second. Okay, and this is analytical because we derive the equation, but it has a limitation because it's only steady state, 0 battery power. Okay, so this can be helpful when you're analyzing, you know, when you're starting to analyze some system, you know, and try to, you know, analyze new systems. Okay, but usually this approach is valid at high speed, because if you think about it, at high speed, usually you drive steady state because you're cruising. You know, if you're driving a highway, you're relatively operating at steady state, right? But when you're driving in urban environment, you have a lot of go and stop, right? So low speed analysis is not quite accurate. So this analysis is not valid for low speed, okay? Any questions? Oh, by the way, is my voice too loud or too, or just fine?
것
Am I
같습니다.
yelling? 제 소리가 너무 크진 않나요?
적당한 것 같습니다.
아, 그래요? 소리 안 들릴까봐 좀 목소리를 크게 내고 있거든요. And this slide compares different design or even different architecture. To make different alpha, you might need different architecture, okay? Anyway, so when alpha changes, the location of generator changes, okay? And what happens when alpha changes? So this was Prius, but when alpha changes, where is so this is alpha equal to 4, and okay, alpha equal to -2, okay? So when you change this gear ratio or change architecture, you can actually change the speed operation and also torque, right? But interestingly, if you look at power, it doesn't change. Why is that? Well, if you think about it, we had this constraint, right? PA equals to PB. And then that becomes, you know, function of Rn. So it's function of Rn. So when independent variable Rn is determined, then your power is determined, and the freedom you have is now speed and torque. So you can do these type of analysis, without, optimizing, the controller, without, simulating or optimal control. Okay. Very fast, very simple analysis. Okay. But not very accurate. Okay. And if you move on to compound splits, things become a little more tricky. Okay. Now you have 4 equations, and then you have now 2 mechanical points. And then let's say we still want to have the independent variable as Rn, the gear ratio or speed ratio. And then we have one more variable, which is ratio spread. So this is basically the ratio between alpha and beta. Or let's look at this one. How spread this alpha and beta is. We might have this lever, or we have this kind of design, right? So we need to somehow be able to, analyze what happens when this spread changes. Okay. And that's this variable, which is only valid for compound lever. Okay, compound split. So if you do the same analysis, normalize speed, torque, and power, then you get these equations. And then you have torque. You also use this no battery power assumption, and then you can compute, all of this. Please, take a look. And this is the final resulting 4 equations. Okay. Omega A with respect to omega I, omega B with respect to omega I, torque A with respect to torque input, torque B divided by torque I. So normalized by input. Okay. And again, alpha and beta is given, and Rn is independent variable, and then everything can be determined. By the way, for beta equal to 0 case, input split, if you put beta equals to these equations, then you get these equations, which is identical to these equations. Okay. So here we just used beta equals to 0 from the beginning. And then we can start from here and then use beta equal to 0 or alpha equal to 1, whatever. Okay. All right. So we newly defined ratio spread, which is phi. So when alpha is 2 and beta equal to -1, phi becomes 4. When alpha is 4 and beta equal to -2, then phi becomes 2. So this is wide ratio spread, narrow ratio spread. So oh, I'm sorry. I guess this is wide and this is narrow. Maybe narrower. Okay. So how far is this 2 points with respect to 1? Okay. And we can do some analysis about different phi values, just like we did an analyze for different alpha values, right? So we can do the same thing for different phi values and see how things change, right? But I'm not going to go too much into this detail, okay? I think this gets a little too, complicated and focusing a lot on, compound split architecture study. I think, but I wanted to, I want you to learn about this methodology, analysis tool, okay? So that these tools are available and you can do these type of analysis. And we can also talk about gear shift or mode shift. So Allison hybrid, the 2-mode, had 2 modes where low speed mode is the input split and high speed mode was compound split. So you have 2 mode, and if you have to go from one mode to another, that means it's a it's like gear shift, okay, or mode shift. So we can do the analysis for input split with speed reduction gear or torque multiplication, okay. So you have higher torque for low speed, okay, which is low speed mode. So same methodology, same approach. You can do the same, but now you have the second PG, which is the speed reduction gear or torque multiplication gear. So torque is multiplied at the output, okay. And if you do the same thing over for compound split and input split mode, and then if you plot, this is what happens, okay. And we're assuming so it's a good idea to shift at the common mechanical point, because mechanical point is supposed to be efficient, because there's no power circulation. There's no the electrical power flow becomes small, so efficiency is good. So you want to operate near mechanical points. And for compound split, we have these 2 mechanical points. For input split, we have this is the mechanical point. So we have this common mechanical point, and that's this point. This is 9/4. So this now becomes high speed, which is compound. This becomes input. So we can also do two-mode analysis using these tools, okay? But you can see when mode changes, the behavior changes, right? So I guess this could supposed to be like this, but now we are doing this, right? And also, anyway, so I think this should be good for now.